Hello dear friends, welcome to the lecture of differential calculus. In this lecture we shall solve some problems on verification of Rolle's theorem. In the last lecture we have studied the statement of Rolle's theorem, its proof, and also the geometrical interpretation of Rolle's theorem. Now Rolle's theorem states that if a function f of x is continuous in the closed interval a comma b, the second condition is it is differentiable on open interval a comma b, and the third condition is the values of the function at endpoints f of a is equal to f of b. Then there exists at least one value c in the open interval a b such that f dash of c is equal to 0. This is the statement of Rolle's theorem. There are three conditions. First is f of x is continuous in closed interval a b. Second, derivable in open interval a comma b, and third, f of a is equal to f of b. Then there exists at least one value c in the open interval a b such that f dash of c, derivative at that point c, is equal to 0. So this is the Rolle's theorem. Now we have to verify this theorem for these some functions are given in these problems. I have written the problems here, and we have to verify Rolle's theorem for these functions one by one. The first is f of x is equal to log of x square plus ab divided by a plus b times x, and the interval is again general interval a comma b, closed interval a comma b. Whether Rolle's theorem is satisfied or verified for this, whether it is applicable, or the problem may be asked as discuss the applicability of Rolle's theorem for these functions. Now the function first is f of x is equal to log of this expression. So first we have to check the three conditions of Rolle's theorem. If the three conditions that are here, f of x is continuous in closed interval a comma b, derivable in open interval a comma b, we know the difference between closed interval and open interval. Here the endpoints are not included, and here the endpoints are included in the interval and all the in between points. Third condition of Rolle's theorem is f of a is equal to f of b. So we have to first check these conditions. Then if these three conditions are satisfied, then the theorem can be applied, and by the theorem there exists at least one value, maybe more than one value. At least one value c belongs to the open interval a comma b such that derivative at that point is equal to 0. So this is the Rolle's theorem. Now we shall check whether this function log of that expression is continuous in the interval a b or not. So we know some standard functions, continuity of some standard functions. Logarithmic function is continuous for all positive real numbers, and therefore the function here is continuous. If x is or this expression is positive, then it is continuous. So therefore this function is continuous in the given interval a b, that we shall first mention, and we can find the derivative of that function. Then it is derivable. So it is also derivable, and we shall check the third condition, that whether the f of a is equal to f of b. So we shall start the solution for first problem. That is f of x, given function. Given function is, we can simplify f of x using law of logarithm. This can be written as log of x square plus ab minus log of a plus b times x. This is the given function, or we may number this as first equation. and these are continuous, both functions, and by algebra of continuity of functions, difference of two continuous function is also continuous. So since logarithmic function, we can write the reason, since logarithmic function is continuous in the positive real numbers, that can be written as 0 to infinity. And we may see that if a, b are real numbers, then this quantity is positive. Both are negative, then this is also positive. Square is positive. So therefore this is a positive value, and logarithmic function is defined and is continuous. So here also if this is a positive quantity, then it is defined also and it is continuous. So logarithmic function is continuous in the interval 0 to infinity. F of x is continuous. Continuous in the interval AB. Now here we have to assume this as say interval AB, where the logarithmic function will be continuous. Now the second point is, second condition of Rolle's theorem is whether it is derivable or not. We can differentiate this. Now f dash x is equal to derivative of f of x, derivative of log of this. We know derivative of log x is 1 over x. So therefore this will be 1 over x square plus ab into derivative of x square plus ab by chain rule, which is 2x plus 0, or that is 2x. So therefore that derivative we shall write directly, that is 2x divided by x square plus ab. You can check it easily. Derivative of this function minus. Now similarly we see what will be derivative of log of a plus b into x. So that will be 1 upon a plus b into x and multiplied by the derivative of this bracket, which is a plus b, or that will be actually a plus b divided by a plus b into x. Now see, this term cancels or this term divides, and we get only 1 by x, and this can be simplified as we take the LCM as x into x square plus ab. This term is cancelled, x remains, product of these two, and now x into 2x, that is 2x square, and here it is 1, and x square plus ab, that is negative sign is there, minus x square minus ab, or which will be x square minus ab divided by x into x square plus ab. And see, this quantity exists, this exists, f dash x exists in the interval AB, open interval AB. So when this will vanish, only the denominator is 0, and we are assuming this as this quantity as a and b non-zero, and therefore so this is not 0 and the quantity exists. So that means f dash x exists in the open interval AB. F dash x exists in AB, and that is the second condition. So this is the first condition of Rolle's theorem. This is the second condition, derivative must exist. So therefore it can be written as fx is derivable in open interval AB. Now what about the third condition of Rolle's theorem? We have to check f of a is equal to f of b or not, and that we can see from 1. From 1 what is and we shall have to use this f dash x. We suppose this as second equation. This is our first equation. Next, f of a is from this, you see, a log of, in place of x we have to write a square plus ab that is log of a square plus ab minus log of, and you see a plus b into a, that is again a into a square plus ab, and certainly this is 0, equal values and their subtraction. F of b is again x is b, so b square plus ab minus, that is log of again ab plus b square, that is same as b square plus ab. You can check this easily, b square plus ab, and so this is 0. That means the third condition of Rolle's theorem is also satisfied. These values are equal. F of a is equal to f of b, and thus, or therefore we can say f of a is equal to f of b, and hence thus the three conditions of Rolle's theorem are satisfied. Thus all the three conditions of Rolle's theorem are satisfied. And if these conditions are satisfied, then what the Rolle's theorem states, there exists at least one value c in the open interval ab such that f dash c is 0. So that we have to verify, and therefore we have to find c. Therefore we have to find c belongs to open interval ab such that, I shall write below, such that f dash of c is equal to 0. Now from second we have to use this value, derivative is required, so that's why we have written this equation as equation 2. Now from this, what is the f dash of by 2? By 2, what is the f dash of c? Replace x by c, that will be c square minus ab divided by, in place of x we have to write c into c square plus ab, and that is equal to 0. So c is non-zero, and therefore this is non-zero quantity, and if you transfer this or multiply both sides by this denominator, then we shall get c square minus ab is 0. So this is 0 means the numerator must be 0. So this implies c square minus ab is equal to 0, or that means what about the value of c? C is under root of ab, or therefore this implies c is equal to root of ab. And what we have to verify, whether this value is in the open interval a comma b or not. This value of c is in the interval a b or not, and this is geometrical mean of a and b. So product of two quantities and its square root is a geometrical mean, and the geometrical mean lies in between a and b. So this belongs to open interval ab, and hence the theorem is verified. So this is the statement of the theorem. We have to obtain, therefore we have to find c, and we have obtained c, and that is in the interval, open interval ab. So hence Rolle's theorem is verified. So this is, in this way we have to verify the theorem. First check the three conditions of Rolle's theorem, and then find the value of c and show that that value is in the interval, open interval a comma b. Theorem is verified. So this is the procedure to verify Rolle's theorem. Now we shall consider the second example, solution for second. So what is the given function is the same as f of x is equal to, in the similar way we shall consider the given function as f of x, and that here for the second problem it is sin x divided by e power x in the interval x belongs to 0 to pi. Here a is 0 and b is pi. So we shall suppose this f of x as 1. Equation 1. that we shall consider. And now we will check the conditions of three conditions of Rolle's theorem. Whether the function is continuous in the closed interval, that is the first condition. So see, the function is the quotient of sine x and e power x, and both these functions are continuous. Trigonometric functions sine and cos are continuous everywhere for all real numbers. This exponential function is continuous for all real numbers. Both these functions are continuous. Their division, their addition, subtraction, multiplication and division of continuous functions is also continuous. So that we can just mention in one statement, since sin x and e power x are continuous functions on real number or in the interval minus infinity to plus infinity. F of x is continuous. Continuous in the closed interval 0 to pi. So this interval is part of this interval. This is, or it is a subset of this interval 0 to pi, and it is minus infinity to infinity, all real numbers, and this is a finite subset of this set of real numbers. And if the function is continuous everywhere, it is also continuous in the interval 0 to pi. And now we shall find out the derivative of this. So the first condition is satisfied. Conditions we have to check for whether these are satisfied or not. Next, f dash x is, or now f dash of x from 1. Here it is a quotient, and we shall apply the quotient rule of derivative, or derivative of quotient. So that will be e power x into denominator into derivative of numerator, that is cos x, minus the numerator, that is sin x, into derivative of denominator, that is again e power x. Quotient rule we are using of derivative, and divided by denominator square. So square of this, and again see, e power x is common and one term from denominator cancels. What remains is cos x minus sin x divided by e to the power x, and this is, we shall suppose, second, that is the derivative f dash x. And now you see whether it exists in the open interval 0 to pi or not. Yes, it exists, because when the quantity does not exist, if the denominator becomes 0, and this exponential function is never 0, it will tend to 0 for x at minus infinity, but we have to consider the open interval 0 to pi, and therefore this f dash x exists in open interval 0 to pi, and that means fx is derivable. F of x is derivable in the open interval 0 to pi. Second condition of Rolle's theorem is satisfied. Now what remains is the third condition. What is the third condition? Whether the values at the end of the intervals are equal or not. F of a is equal to f of b or not. And here a is 0, b is pi. Next from 1. F of 0 is equal to function's value at lower end 0, sin 0 divided by e power 0. Sin 0 is 0 and this is 1. So therefore the value is 0. And what is f of pi? That is sin pi divided by e to the power pi. We know sin pi is also 0. So 0 divided by e to the power pi. This value we don't know, we can, but it is not 0. Denominator is not 0, so it exists, and that value is again 0. So thus f of 0 is equal to f of pi, and all the conditions of Rolle's theorem are satisfied, all the three conditions. So therefore, thus all the three conditions of Rolle's theorem are satisfied. Conditions are satisfied. We are not saying that the theorem is verified. It is yet to be verified. First check the three conditions, and then if these three conditions are satisfied, then the theorem assures that there exists a value C. So I shall write now below. Therefore, there exists, or we have to find, therefore we have to find C belongs to open interval 0 to pi, open interval 0 to pi, such that f dash of C is 0. And by 2, what is f dash of 2? F dash of C, replace x by C. So that is cos C minus sin C divided by e to the power C. Replacing x by C is 0. So this expression is 0, and this is not 0, therefore the numerator must be 0. So we cross multiply, 0 into e power C is 0. So this implies cos C minus sin C is 0. Cos of C minus sin of C is 0. And that means cos C must be equal to sin C. Now for which angle the cosine and sine are equal in this interval 0 to pi? We know that is pi by 4 or 45 degree. So this implies C is equal to pi by 4, and certainly this pi by 4 value is between 0 to pi, and thus or hence Rolle's theorem is verified. After satisfying three conditions of Rolle's theorem, we have obtained the value of C in the interval 0 to pi, given interval, open interval, such that the value of C, f dash of C is equal to 0. Hence, Rolle's theorem is verified. And this completes the solution. So exactly the same procedure we are using for the first problem and the second problem. Now what about the third problem? So third problem is slightly different. You see what is the difference in the first, second and third problem. Here the function f of x is defined by a single definition, but here the function has two definitions. Our function's definition has two parts. It has two values. F of x is x square plus 1 under the condition when x lies in the interval 0 to 1 or closed interval 0 to 1, and it is 3 minus x when x is in this interval 1 is strictly less than x is less than or equal to 2. Means it is a semi-closed interval, open at this end, closed end on the other end. And here we have to also check the function's continuity. But what is the interval? Given function is in the interval. Interval of the function is 0 to 2, 0 to 1 and then 1 to 2, means the entire interval is 0 to 2. Given function fx is in the interval 0 to 2. It is defined in this interval. Now we have to check the function fx is continuous or not. So this is a polynomial function x square plus 1. It is continuous in this interval. And 3 minus x is also continuous in the interval 1, 2. Then what happens about the continuity? The function is continuous at every point except possible at point 1, because at point 1 it changes its definition. On the left side of 1 it has x square plus 1 definition, and on the right side of 1, if x is greater than 1, then it has 3 minus x. So the function's continuity we have to check at this point 1, where it changes the definition. Fx is continuous, so we can write fx is continuous in the entire interval 0 to 2 except possibly or except perhaps at x is equal to 1. We have to check. We don't know what about x is equal to 1, whether it is continuous or not, but it is continuous everywhere except possibility of x is equal to 1. May or may not be continuous, that we have to check. Now we know how to check the continuity at a point, or when the function is said to be continuous at point, if its value, function's value at that point, here it is 1, is equal to the function's limit as x tends to 1 from right, and is equal to the function's limit when x tends to 1 from left. So that we have to check. And now we have, from the definition, what is f of 0? F of 0 means what is the function's value when x is equal to 0. So x is equal to 0 is in this interval. So we have to use this definition of the function. So here put x is equal to 0. So it will be 0 square plus 1. F of 0 is 0 square plus 1, which is 1. And now limit as x tends to 1 from right. This is the notation to write limit from limit of x tends to 1 from right. When x is greater than 1 and approaches towards 1, then that is right hand limit of f of x is equal to limit x tends to 1 from right. Which value of the function, which definition of the function between these two is to be used? That is important, and that is to be noted and to be understood. So x greater than 1, x tends to 1 from right means x is greater than 1, and x is greater than 1 is the interval where it is, here it is. 1 is less than x means x is greater than 1, and therefore this definition is to be used, and we should write f of x value as 3 minus x. And what is this value? Now we can put simply x as 1, 3 minus 1, and which is equal to 2. So the right hand limit is 2. Next is limit x tends to 1 from left of f of x, and this is equal to limit x tends to 1 from left means x is less than 1, and x is less than 1 is in which interval? See, x is less than or equal to 1 means this interval, and for this interval the definition is x square plus 1. So therefore we have to use the value of f of x as x square plus 1, and this is, now it is direct. So these are the notations for left and right limits, and not, this is, you should note, this is not minus 1, it is x tends to 1 from left. And but when we substitute the limit, we have to put x is equal to 1 only. So therefore this becomes 1 square plus 1, or which is equal to 2. And thus we can now see f of 0 is 1. Now f of 0, what we have is f of 0 is 0 square plus 1. And what is the limit? See, it is the point should be x is equal to 1, not f of 0. We have to obtain f of 1. So this is to be corrected. We are checking the continuity at x is equal to 1. So this must be f of 1. And 1 is in this interval. X is equal to 1 is in this interval. And then, so we have to put x is equal to 1. So 1 square plus 1. So this should be corrected. This must be corrected, and you should note this. 1 square plus 1, and 1 square plus 1 is 2. Now you see, f of 1 is to be obtained. So we are checking the value at x is equal, continuity at x is equal to 1. Now all the three are equal. F of 1 is to limit of fx as x tends to 1 from right, and limit of fx as x tends to 1 from left, all are equal. And this is the condition for continuity. So, or thus we can say, so we see that f of 0 is same as limit x tends to 1 from right, and is limit x tends to 1 from left of f of x, and therefore f of x is continuous at x is equal to 1. Is continuous at x is equal to 1. and hence or thus f of x is continuous in the closed interval 0 to 2. So only there was a doubt about x is equal to 1, and that we have checked. At other points it is certainly continuous, and therefore the function is continuous in the closed interval 0 to 2. Now what about derivable, whether the function is derivable or not? And for that purpose we shall consider next, we have derivative of f of x. And that is f dash x. F dash x is equal to. Now we see that we can differentiate this. What is the derivative of x square is 2x. Derivative of 1 is 0. So it is 2x when x is in the interval 0 less than or equal to x less than or equal to 1. And this derivative is 3 minus derivative of 3 is 0. 0 minus derivative of x is 1. So that is minus 1. When 1 is less than x is less than or equal to 2. Again the function is having derivative 2x and that is that exists in this interval. Whatever the value of x is between 0 to 1, this value exists. And similarly whatever the value of x between 1 to 2, this value is constant, that is minus 1. So that is the derivative exists in the interval, open interval 0 to 2, except possibility at again x is equal to 1. So the derivative fx is differentiable or f dash x exists. F dash x exists in the interval, open interval 0 to 2, except possibly or except perhaps at x is equal to 1. So that means we have to check the derivative, the function is differentiable or not. Earlier we have checked the continuity at x is equal to 1. Now we have to check the differentiability at x is equal to 1. And when we say the function is differentiable at a point, if its right hand derivative is equal to left hand derivative, then it is differentiable. Otherwise the derivative does not exist, and for that purpose we shall obtain the right hand derivative, and this is the notation. R means right hand derivative of f at 1. So R f dash at 1, and by definition it is limit h tends to 0 from right. So we have seen this earlier in the chapter of differentiation, a condition when the derivative exists and what is the meaning of right hand derivative and left hand derivative, and it is f of 1 plus h minus f of 1. F dash of c, we have f of c plus h minus f of c divided by h, and that is limit h tends to 0 from right. Now what is f of 1 plus h? What is important here is we have to use the proper definition of f dash here. It is f dash, definition for f dash, but here it is f. So proper definition of f is to be used, means from this, the given original function f of 1 plus h. H is positive value, h has positive. So this means it is greater than 1, and greater than 1 the function is defined by 3 minus x, and so we should use this as f of this second definition 3 minus x, that is 3 minus x is here 1 plus h. Second definition of function is used because it is this quantity is greater than 1. And what about f of 1? F of 1 we have obtained earlier in the first part of continuity. F of 1 means here it is x is equal to 1 and 1 square plus 1 is 2. So f of 1 we have obtained as 2 earlier. So this is 2 divided by h, and that value is, now you see. So what will be this value? This is equal to, so I shall write here, this is equal to 3 minus 1 is 2, 2 minus 2 cancels 0, and what remains is minus h divided by h. Limit h tends to 0 from right, minus h divided by h, or that is minus 1, and thus it is a constant and this value is minus 1. H cancels actually, we don't put 0 here, it cancels and it remains limit of minus 1, limit of constant is constant. So that is r of right hand derivative of f at 1. Now further is L, f dash of 1 means left hand derivative of f at 1, and the definition remains similar, but the change is here h tends to 0 from left. Limit h tends to 0 from left, f of 1 plus h minus f of 1 divided by h. This expression remains the same, only the change in the limit, h tends to 0 from left, and what makes the difference here is limit h tends to 0 from left, f of 1 plus h, h here is negative, h is less than 0, and if h is negative this quantity becomes less than 1, and when the quantity is less than 1, so we have to use the first expression of function, first definition of the function, x square plus 1, and in place of x here is 1 plus h. So therefore this expression will be 1 plus h whole square plus 1. So this much is the function's value. F of 1 remains fixed, that is minus 2, divided by this h is also the same. And now see, simplify this. What is this expression? It is limit h tends to 0 from left, and if you expand this, it is 1 plus 2h plus h square and plus 1. So that 1 plus 1 is 2. So and that 2 cancels with this 2. So what remains is the middle two terms, 2h plus h square divided by h. And if you take h common and cancel that h with the denominator, divide by h both, numerator and denominator, and what remains is limit h tends to 0 from left. And if you, after dividing both numerator and denominator by h, it remains 2 plus h, and this limit, as we see, h is 0, so it is 2. And now we see, this is the left hand derivative is 2, right hand derivative is minus 1. Whether these are equal? Certainly not. Minus 1 is not equal to 2, and therefore r f dash of 1 is not equal to L f dash of 1. And if these are unequal, we say the function's derivative does not exist. F dash 1 does not exist. Therefore f dash of 1 does not exist, and if it does not exist means the function is not derivable at x is equal to 1, and x is equal to 1 is a point in the open interval 0 to 2, and therefore we say the function is not derivable in the open interval 0 to 2. Thus f of x is not derivable. In the open interval 0, 2, because it is not derivable at one point x is equal to 1. When we say it is derivable, it must be derivable at every point from 0 to 2 except 0 and 2, and it does not satisfy this condition. So hence the second condition of Rolle's theorem fails. The second condition of Rolle's theorem fails, and if one of the condition fails, the theorem cannot be applicable, and that means the Rolle's theorem is not applicable for this function. So we can say Rolle's theorem is not applicable. not applicable for f of x. So this is the conclusion for this problem. Here we can't apply the theorem because second condition fails. If one of the condition fails, we say the theorem is not applicable. And if all the conditions are satisfied, so there is no need to check the third condition. What is the third condition of Rolle's theorem? F of 0. Now what is f of 0? It is 1. And here 1 here, f of 0 is 1. And what is f of 2? For this, f of 0 is 1. And f of 2 from this, 2x is equal to is this, 3 minus 2, that is also 1. Third condition is satisfied, but the second condition fails. So because the second condition fails, there is no need to check the third condition, and hence we have written that Rolle's theorem is not applicable here. But one thing is to be noted, or we write it as a remark. The Rolle's theorem's three conditions of Rolle's theorem are sufficient but not necessary. So without satisfying none of the conditions, there may exist a value c in the open interval AB such that f dash of c is equal to 0. So that we shall write as a note or as a remark. The conditions of Rolle's theorem or the three conditions of Rolle's theorem are sufficient. Means if these are satisfied, then there exists certainly exists c belongs to AB such that f dash of c is 0, but are not necessary. What is the meaning of they are not necessary? Without satisfying the conditions, there may exist a value c in the open interval AB such that f dash of c is equal to 0. That is to be noted. The conditions are sufficient but not compulsory or not necessary. And thus we have solved the first three problems. Now I will leave these problems 4, 5 and 6 for you to solve. See, for this function the value of c is pi, which is in the interval. That means the Rolle's theorem is verified for this function. We have done the steps. You do this go by the similar way and you will get this value of c. Now what about the fifth function? This is not applicable, means one condition is not satisfied. One condition of Rolle's theorem is not satisfied, and you should check that condition. It is again the second condition is not satisfied, means the derivative does not exist. At which point it does not exist, that you should see. And for the last one, this is a product of the two algebraic terms, or it is a polynomial. It is continuous, it is differentiable, and the value of x is a f of a is 0, f of b is 0. So all the three conditions of Rolle's theorem are satisfied, and therefore there exists the value, and that value is this one, mb plus na divided by m plus n. So it is a formula, section formula. It is a point which divides AB in the ratio m to n, and therefore it is in between the interval AB. So that means here the theorem is verified, and this is here the theorem is not applicable. So try to solve these problems yourself, and the remaining part we will continue next time. Thank you.